Let's now revisit the quantitative data set on the dollars spent on music per year by a group of 20 students. The reason this is called quantitative rather than qualitative is because not only is the data numeric, but arithmetic makes sense. So for example, somebody that spent $137 spent less than someone who spent $214, for example. Or you can actually do subtractions. Somebody that spent 85 spent 40 more than the person that spent 45. So we have this quantitative data, and so far we've talked about summarizing this data. We've summarized it in a couple of ways. You should be able to make a histogram with this type of data. You should be able to make a frequency polygon. You should be able to make an ogive. And we should also be able to make a stem and leaf plot, although we'll deal with simpler data than this one here for the stem and leaf plot. However, we want to be able to describe it in non-graphical ways. So all these are graphical representations of this data. We want to do it with numeric computations as well. And we saw numeric computations in our frequency tables, but we need some other things. We are going to first focus on measures of central tendency, the centers of the data, if you will. And you've likely heard of all three of the measures of central tendency that we're going to focus on. They are the mean, median, and mode. Let's first start with the concept of mean. We start with the mean. Many of you already know about the mean, and the most common word used to represent the mean in the common language is average. Finding the average of a set of data is finding the mean. In reality, the mean, median, and mode are all averages. Measures of central tendency are all called averages. However, in common language, people use the word average to represent specifically the mean. So let's go through and talk about computing the mean of this set of data. You probably pretty easily remember that to find the mean, you add all the data points and divide by how many there are. That's the informal definition of the mean. Now we're going to do that with this particular set of data, but let's first discuss some notation that is not only important in this section, but will be important throughout the entire course. So it's very important that you learn this notation. First, we distinguish between talking about a population mean and a sample mean. Remember, population mean would be a parameter because you're doing a computation with all of the data, whereas a sample mean would be a statistic because you're only doing a computation with a sample or subset of the larger population. So let's go through first what the meaning is of these formulas here and all the notation in here. And then we'll end up getting to actually computing the mean of this set of data. First off, this is the Greek letter mu. It's pronounced mu with like a long U to it. Mu is the population parameter for mean. Again, this is for the population. So mu, whenever we use it in this course, represents the population mean. X bar is how we read this. So it's an X literally with a bar over top of it. X bar represents the sample mean. So those two notations are extremely important and will play a role throughout the entire course. Now let's analyze each of these formulas. Notice we've got the sigma sign in here. Again, sigma represents a sum. Not surprising that we're asking for a sum because, as you can see, your informal understanding of a mean is to add up all the data points. So we want to add all the data points. That means this X represents the data points, and you can see that down here. The raw data values are these values X. So the mean, the population mean, is equal to the sum of the data values divided by this capital N represents the size of the population. So you're dividing by how many there are, or the size of the population. With the sample mean, you've got X bar represents the sample mean. It's equal to the sum of the data points divided by lowercase n represents the size of the sample. So you're dividing by n, which represents how many data points there are. We will practice with this notation throughout the course. So let's actually now do the computation. Let's treat this as if it is a sample. It could be potentially a population, but let's treat it as a sample. Let's find the mean. So first thing, to use proper notation, we're looking for X bar. Well, the first thing we need to do, according to this formula, is to add up the data values. If you go through and add up all these 20 data values, you get a total of 4,977. And then according to the formula here, we need to divide by n, lowercase n, which is the size of the sample. And there's a total of 20 data points here. So we want to divide by 20, and we get that this is approximately equal to 248.85. We've computed the mean value. The mean value of this set of data is $248.85. That's the mean amount of money spent on music per year. Let's now move on to finding the median of the dollars spent on music per year. The definition of median is right here. Once the data is put in order, ascending or descending, doesn't matter, but it needs to be in order, the middle data value when n is odd is the median. If you have an even number of data points, then you take the average or the mean of the two middle numbers and count that as the median. So the median essentially represents the middle. So notice already I've got this data here sorted in ascending order, and now we need to find the middle point. Again, since there's 20, there's going to be 2 points in the middle, and the 2 points are in the 10th and 11th position. Here's the 10th value, here's the 11th value. Notice to the left of that, there's 9 data values to the left of that, and there's 9 data values here. So the 200 and the 214 are the middle two numbers. To find the median, we then take the mean of those two. So we're going to add 200 to 214, and we're going to divide by 2. And we get a total of 207. The median value of this set of data is 207. Let's now get the mode of this set of data. The mode, by definition, is the data value with the highest frequency. And if you go through and look at all these, the highest frequency data value is the 0 because it showed up 3 times. So the mode in this case is 0. Now you might be wondering, why do we compute a mean, median, and a mode? Why not just one over the other? Well, first of all, notice that they're all very different. The data set here had a mean of 248.85 approximately. It had a median of 207. And it had a mode of 0. Very different numbers here. We will talk in a coming slide about the importance and the meaning of each of these individually. Right now, we just want to make sure you can do the computations. It also should be noted that a mean can only be computed for quantitative data because it requires adding up a set of numbers. With qualitative data, you can't add up those values. It doesn't make any sense. The arithmetic doesn't make sense. So mean can only be computed on quantitative data. Median can also only be computed on quantitative data. It requires you putting the numbers in order. Well, there is no order relationship on qualitative data. So median can only be computed for quantitative data, but the mode can be computed for quantitative or qualitative. For example, if you had the car makes of all students in the class, that's qualitative data. You could find the mode of the car data by finding out which car is driven most by the students. There's also one other piece of information that should be noted here before we move on. It is possible that you could have more than one mode. If there's 2 modes, we call the data set bimodal. So for example, let's pretend that there was another 200 here. In that case, the mode would be both 0 and 200 because there'd be 3 200s and 3 zeros. It's also possible that the set of data has no repeating values. In that case, we would say that the data set does not have a mode. We have a couple more computations with respect to mean that we need to focus on. Suppose you wanted to find the mean of a data set, but you didn't actually have the raw data. If you can recall from a previous screencast, we grouped the data for the amount of dollars spent on music per year into 7 class intervals from 0 to 99, 100 to 199, all the way up to 600 to 699. And we created a frequency table. There were 6 data values between 0 and 99, 2 between 100 and 199, etc. And we also computed the midpoint when we did that, because we used the midpoint on our horizontal axis to make our ogive and our frequency polygon. So let's say you only had this. This information was presented to you in a journal, let's say, and you were not given the raw data, which is pretty likely. Most researchers do not give out the raw data, they just give out the summaries. So let's say the researcher presented you with this information, but did not give you the mean. We want to be able to get an approximation of the mean from this frequency distribution table. And the way we do that is over here. We have to take the sum of x times f. In this case, x is not representing the raw data values because we don't have them. X is actually representing the midpoint itself. All right? Times, we need the frequencies, f stands for frequency, and then we divide by the total number of data points. And because we don't have the raw set of raw data, we can't simply just count how many there are. Instead, you would just add up these frequencies. That tells you how many data points there are total. So in this case, sigma f is equal to 20. And we already know there were 20 raw data points, so that should make sense. So let's run through this computation. By the order of operations, to do this computation, we need to first do the multiplication of x with f, because the multiplication of x and f is set off in parentheses. So we first need to find that product. Let's just simply add on to this table. We have x are our midpoints, f are our frequencies, and we need to multiply those two columns. So I'm going to create a new column with x times f on it, and we'll put these numbers in. And the first product is 297. 6 times 49.5 is 297. And the next one is 299. The next is 748.5. The next is 1,398. The next is 899. 549.5 is the next, because 1 times 549.5 is just 549.5. And the final one is 1,299. So we just did the computation of all the x's times the corresponding f's. The next operation we need to take care of is the sum. We need to take the sum to get this numerator here. So we needed the sum of the x times f's. So we need the sum of the x times f's, and we get 5,490. Our final move then is to take that number and divide it by sample size, which is sigma f, which is this. So we're going to take 5,490 and divide it by 20. And we get x bar is approximately equal to 274.5. Remember, this is an approximation of x bar. When we did the computation of x bar in one of the previous screens, we got that x bar was equal to 248.5. Now, of course, this one is better because that's exactly what the mean is. But if you don't have access to the raw data and can't get this, this is the next best thing. So we can use this formula to approximate the mean from a frequency distribution.